Join us as we explore how James Clerk Maxwell revolutionized our understanding of molecular motion in gases. Before Maxwell, scientists struggled to understand the chaotic motion of gas molecules and their varying speeds. Let's begin by understanding why earlier uniform models of molecular motion were inadequate. Early scientists assumed all gas molecules moved at a uniform speed, but experimental measurements showed this was completely wrong. The uniform model predicted all molecules had identical speeds, represented by this single line, which contradicted all observations. Experimental measurements revealed molecules had a wide distribution of speeds, from very slow to extremely fast. Maxwell approached this problem with brilliant mathematical insight and physical intuition. Maxwell's first key assumption was that the x, y, and z components of molecular velocity are statistically independent of each other. Each velocity component along x, y, and z axes behaves independently, meaning knowing one component tells us nothing about the others. Maxwell also assumed spatial symmetry. There's no preferred direction in space for molecular motion, making the distribution spherically symmetric. Now let's see how Maxwell derived his famous distribution function. From independence, the joint probability is the product of individual component probabilities, each described by the same function g. From symmetry, the distribution depends only on the total speed v, which is the square root of v x squared plus vy squared plus vz squared. Combining these constraints, Maxwell showed each component must follow a Gaussian distribution, g of vx equals a times e to the negative bvx squared. The complete velocity distribution is this elegant expression involving mass m, Boltzmann constant k, and temperature T. However, experiments measure molecular speeds, not velocity vectors. We need to convert this result. Converting from velocity to speed distribution requires considering spherical shells in velocity space. The Maxwell speed distribution is p of v equals 4 pi versus squared times the velocity distribution, where the versus squared factor comes from the spherical shell volume. This is the famous Maxwell distribution, a bell-shaped curve that peaks at the most probable speed and has a long tail toward high speeds. Let's examine the important features of this distribution. The most probable speed is Vmp equals the square root of 2 kt over m, which occurs at the peak of the distribution. The average speed is slightly higher, V average equals the square root of 8 kt over pi m. The root mean square speed is highest of all. Vrms equals the square root of 3 kt over m and relates directly to kinetic energy. These three characteristic speeds are marked on the distribution, with the most probable speed at the peak, average speed slightly right, and RMS speed furthest right. Let's calculate actual speeds for oxygen molecules at room temperature. For oxygen at 300 Kelvin with molecular mass 32 atomic mass units, or 5.3 times 10 to the negative 26 kilograms, the most probable speed is approximately 395 meters per second, faster than the speed of sound in air. The average speed is about 445 meters per second. The root mean square speed is approximately 483 meters per second. These are incredibly high speeds. Oxygen molecules at room temperature move at nearly half a kilometer per second. The true power of Maxwell's theory emerged when it was tested against experimental data. When experimental speed histograms shown as bars were plotted against Maxwell's theoretical curve, the match was remarkably close. Early experiments used molecular beam techniques, allowing molecules to escape through a small hole and measuring their speeds. The agreement was excellent across different gases and temperatures, validating Maxwell's theoretical framework. Maxwell's distribution revolutionized our understanding of matter and laid the foundation for statistical mechanics. This work replaced deterministic models with statistical descriptions, showing that macroscopic properties emerged from statistical averages. It provided the foundation for Boltzmann's work on entropy and the development of statistical mechanics. This statistical approach transformed physics, showing how simple probability rules governing individual particles lead to predictable macroscopic behavior. Now let's explore a modern application: echogenic microbubbles for advanced ultrasound imaging. Echogenic microbubbles are tiny gas-filled microspheres, typically 1 to 10 micrometers in diameter, with a stabilizing shell. The microbubble consists of a gas core surrounded by a thin shell made of lipids, proteins, or polymers that provides stability. Why are microbubbles useful? They provide enormous acoustic impedance contrast between gas and surrounding tissue, making them excellent ultrasound contrast agents. The key to microbubble imaging is their oscillatory response to ultrasound waves. The Rayleigh-Plessy equation describes microbubble dynamics, relating radius changes to pressure differences and fluid properties. When exposed to ultrasound, microbubbles expand during the rarefaction phase and contract during compression, but this response is highly nonlinear. The incident ultrasound wave, shown in blue, produces a nonlinear response in red, containing harmonics at multiples of the driving frequency. The most exciting application is super-resolution ultrafast ultrasound imaging that breaks the diffraction limit. Classical ultrasound resolution is limited by the diffraction limit, roughly wavelength over 2, typically several hundred micrometers. For a 5 MHz ultrasound, the classical resolution is about 300 micrometers, insufficient for visualizing tiny blood vessels. The breakthrough is to track individual microbubbles flowing through blood vessels, localizing each bubble with sub-wavelength precision. The localization precision equals the point spread function width divided by the square root of detected photons, achieving resolutions below 10 micrometers. Super-resolution requires ultrafast imaging to track rapidly moving microbubbles. Ultrafast ultrasound systems achieve frame rates from 500 to 20,000 frames per second, using plane wave imaging instead of focused beams. By tracking each microbubble through many frames, we reconstruct its trajectory through the microvasculature. By accumulating thousands of microbubble localizations over several seconds, we build a super-resolution map of the entire microvascular network. This technology has transformative potential for diagnosis and treatment. In oncology, super-resolution ultrasound can visualize abnormal tumor blood vessel networks, helping diagnose cancer and monitor treatment response. In neurology, it enables visualization of brain microcirculation through the skull, crucial for studying stroke and neurovascular diseases. It allows quantitative assessment of organ perfusion without ionizing radiation, making it safer than CT angiography. Beyond imaging, microbubbles enable targeted drug delivery through synoperation. When high-intensity ultrasound is applied, microbubbles undergo violent cavitation, oscillating and collapsing near cell membranes. This creates transient pores in nearby cell membranes, allowing drugs or genes to enter cells that would otherwise be impermeable. The cavitation energy released is proportional to the cube of bubble radius times the pressure amplitude, making larger bubbles more effective. One of the most exciting applications is opening the blood-brain barrier for drug delivery. The blood-brain barrier normally prevents 98% of therapeutic drugs from reaching the brain, limiting treatment of neurological diseases. Focused ultrasound, combined with circulating microbubbles, creates reversible, localized openings in the blood-brain barrier. The ultrasound focus creates a precisely controlled region where the barrier opens temporarily, allowing drugs to penetrate while the rest of the barrier remains intact. Safety is ensured by keeping the mechanical index, defined as peak negative pressure over square root of frequency, below 0.7. Super-resolution ultrasound provides quantitative metrics of tissue perfusion. Blood volume fraction equals the volume of blood vessels divided by total tissue volume, measuring vascular density. Blood flow equals blood volume fraction times mean blood velocity, quantifying tissue perfusion rate. For example, normal brain cortex has a blood volume fraction of about 3%, while tumors can have values up to 10% due to abnormal angiogenesis. This difference allows quantitative assessment of tumor vascularity for diagnosis and treatment monitoring. Despite its promise, super-resolution ultrasound faces several technical challenges. Patient motion from breathing and heartbeat can blur images, requiring motion correction algorithms or gating techniques. Low microbubble concentration means long acquisition times are needed to accumulate sufficient localizations, typically 30 to 120 seconds. Ultrasound attenuation limits imaging depth, especially at high frequencies needed for resolution, restricting use to relatively superficial organs. Solutions include advanced tracking algorithms, higher but still safe microbubble concentrations, and multi-frequency approaches. The field is rapidly advancing with several exciting future directions. Targeted microbubbles with ligands specific to disease biomarkers will enable molecular imaging at microscale resolution. Researchers are working toward real-time super-resolution imaging, reducing acquisition times from minutes to seconds. Three-dimensional volumetric super-resolution imaging will allow comprehensive mapping of organ microvasculature. Future systems will map complete three-dimensional microvascular networks, revolutionizing our understanding of organ physiology and disease. Integration with MRI or PET will provide complementary structural, functional, and molecular information. Let's summarize our journey from Maxwell's molecular speeds to modern medical imaging. Maxwell revolutionized kinetic gas theory by deriving the molecular speed distribution from first principles, replacing incomplete uniform models. His bell-shaped distribution provided excellent agreement with experimental speed measurements, validating the statistical approach. Modern echogenic microbubble technology applies sophisticated physics to achieve breakthrough capabilities in medical imaging and therapy. Super-resolution ultrafast ultrasound breaks classical diffraction limits, enabling visualization of microvasculature at unprecedented resolution without radiation. The future promises molecular imaging and targeted therapy at the microscale, transforming diagnosis and treatment of disease.